Enthalpy is a state function. This means that it does not matter how the reaction takes place, only the overall change, delta H. So any number of steps can lead us to that Hess's law, which is the law of heat summation. And again, it's just usually referred to as Hess's law. Looks at the overall process being the sum of the enthalpy changes of its individual steps. So you're going to see different ways of presenting this. Calculate the standard enthalpy of formation of acetylene, C2H2, from its elements. So graphite plus hydrogen yields acetylene is the equation we're looking for. So sometimes you get the equation, sometimes you just get this delta H formation. So remember, that is the formation of the compound from its elements in their standard state. So carbon's normally the solid form, graphite. It'd be nice if it was always diamonds, but it's not. Hydrogen and oxygen are the gases that make up liquid water with its heat of formation. So sometimes you'll have to write those equations. They'll just give you the values. But for this first example, we won't do that to you. And then the heat of combustion, so remember, it's a hydrocarbon, so oxygen combined with the hydrocarbon gives CO2, and water is also known. So we're going to use these three values to figure out what the enthalpy formation is for acetylene. So we need C2 as a product, so we're going to reverse equation C, just like in a half reaction. That's going to change the sign of the delta H. So oxygen, carbon dioxide, and water do not appear in the original equation, which means they must be eliminated algebraically. Okay. So here's your first step. We're going from a negative here to a positive here, because we reversed it. The 4 CO2 molecules are present. We need to multiply equation A by 4. So this 4 is going to get distributed to all the parts. So 4 carbons, and you'll see that in the lower equation, 4 oxygens, 4 CO2s, and then we need 4 times this value. Since 2 water molecules are present, equation B has to be multiplied by 2. So again, we're distributing this to all the parts. So 2 times a half gives you 1, and then 2 times each of the ones, and then 2 times your value here gives you the 571.6. So once you do that, you add up all of your equations and cancel the like terms on each side, and then once you do that, your 4 CO2s with your 4 CO2s, 2 liquid waters with 2 liquid waters, and then 4 O2s here plus this O2 here makes up the 5 O2s that we're canceling there. And then it's just a matter of summing these all together and being, again, careful with the sign, because these two are negative. And that gives us a value of 453.2. Now, the equation's not in the form that we started with up at the top, so I need to divide all of it by 2, because heat of formation is based on 1 mole of a formula. And likewise, what's done to the equation is also done to the delta H value. So again, some things are like the half reactions. Here, there's a difference. So when we multiply the half reaction, we don't change the voltage, but here we do change the delta H. So this is our final equation. So the next sample question we have is calculate the heat of combustion for palmitic acid using Hess's law. And the heat of formation for that is negative 124.8 kilojoules. So we have 2 equations here that we need to deal with. So heat of combustion means we need to burn it. So we're going to have plus O2 yields CO2 plus water. So that's our target equation. And we balanced this on the last one. So we need 23 O2s and 16 CO2s and 16 water. So this is what we're trying to find. Now the other thing we're going to have going for us is this heat of formation. So that's going to be carbon plus hydrogen, again in its gas form, plus oxygen yields C16H32 O2. So I'm going to have 16 of these, and one O2, and that value is negative 124.8. So I just need to manipulate all of the equations I have here and these guys up here to be able to solve for this equation. So the first thing you'll notice is that this C16H32O2 is on this side in the heat of combustion, but it's on the product side in the heat of formation. So first thing I'm going to do is flip that equation. So I'm going to have C16H32O2 So when I flip that, I just reverse the reactants and products, and I get a value of 124.8 kilojoules. That's positive since I'm reversing that reaction. Next thing I see is that I have 16 carbons here that I need to get rid of. So if I go back up to this equation, I can do 16 times this, and then distribute that the whole way through all of that. I'm going to write that below. So when I distribute that 16 the whole way through that equation, I get 16 carbons, 16 oxygen, 16 CO2s, and 16 times this negative 393.5 is negative 6,296.0. Now, it might look like I have an extra sig fig here, but if you look, this is to the tenths, and 16 is a whole number, so I can basically list these in a column 16 times and use the addition rule to keep that tenths place value. Okay. The other thing we're looking at is we have 16 hydrogens, so I need to balance those 16 hydrogens, so I'm also going to multiply this equation times 16 and distribute that one through the entire equation. So 16 hydrogens, 8 oxygens, 16 hydrogens, and then 16 times the minus 241.8 kilojoules. Okay, now I'm ready to cancel like terms. So I have 16 carbons on both sides. I'm going to cancel that. I'm not going to cancel the oxygens yet. 16 hydrogens, 16 hydrogens. So 16 plus 8 is a total of 24. I have to delete one here. So this gives me my 23 O2s. And then if you look, we have what we need. One of these. We have the 23 oxygens and the 23 oxygens, the 16 CO2s, the 16 CO2s, 16 waters, and 16 waters. So then all I have to do is sum these, and that gives us negative 10,040. And I don't have to divide this one out because this is already based on the 1 mole that I have here. So this one we can just leave as our final answer for this problem. Okay, I'm going to stop the video here, and I'm going to do that next question as its own problem.